My name is Mei Chen. My team owns the .NET language and runtime, so including C#, VB, language and compiler, and also runtime team. Yes, all the runtime services that Miguel just mentioned is underneath my team.
Hi, I'm Sergey. My team is on Mei Chen's team, and I lead. And my team owns various low-level parts of .NET runtime and various ahead-of-time compilation technologies.
Sergey is my performance architect. Okay, then let's start. Do you mind to go to the next slide? So what is a runtime? I think it's probably quite obvious to you guys. I prepared this slide for some not sure about the audience. This talk has been done once already. I think about runtime being a translator. If you think about it, you write your C# code once, you compile it once, and it actually runs in all the different devices and different platforms. That is because the runtime is doing the translation for you. We have two well-known platforms and really popular, Windows, Linux, 4 different architectures, x86, x64, ARM64. And if you look at the matrix, there's 8 different languages that runtime speak. And the Linux distro depends on the different distro, different flavor. There's actually platform dependency work that runtime has to do as well. So this talk is going to be 3 parts. First part, we want to talk about how we tune the runtime for startup and throughput, so that out-of-box installation that you have on the .NET Core or desktop is actually performing. The second part, Sergey will walk us through a startup time case study. And the third part, we will do some sort of takeaway. So before I jump into the journey, I kind of want to break down, call out 3 different services in runtime that actually related to today's talk. There are more than these 3 services in the runtime, but these 3 actually kind of relevant to today's talk. I think JIT and GC are probably the most well-known components that you are familiar with, because these are the 2 parts mostly contribute to the non-determinism and latency and kind of manifest itself more in the performance on people's space. The first one is your type system. We don't talk about it a lot, but actually type system is the central of the universe. I would like to believe so, because my first lead job was type system. It was actually the one that holds the universe together. Type system is the one that if you look at this kind of skeleton code, type system is the one decide that when you allocate my base or my class, how big that object instance should be. And when you have vtables, what does the layout look like? And when you do castings, are you doing the right thing or not? So JIT actually consult type system in order to generate code. And GC actually consult type system as well when you're trying to walk the graph. Next slide, please. So here comes to my first question. Many of you are probably very familiar with this HelloWorld WebApi question. This application is quite simple, just a few lines. Pretty much on a web page, pop a hello world and waiting for you to type a string in and display on that page. Do you guys want to guess how many methods need to be JITted in order to run this code? Miguel, since nobody volunteered.
It's an MVC app?
It's a, yep.
So a MVC about 10,000.
Okay. Miguel is very pessimistic. And I must clarify this on .NET Core, because the desktop and .NET Core is different. Next slide, please. It's only 4,000, not too many, but certainly it's greater than what you have expected. Miguel is pessimistic. But if you look at the time, the startup is actually, hot startup is 1.38 seconds. And this is actually measured on the machine that is actually i7, Intel i7, 3.4 gigahertz. It's actually quite a beefy machine. So think about that if you go into a low-end devices or, the less capable machines, how long it will take. And we actually spent 1.49 seconds in JIT, which kind of surprises you, because how can JIT time greater than the startup time? Because multi-core. And that was actually summed together. So we have a problem here. Hello World take 1.38 seconds to start up. this is not okay because real world application is going to use a lot more function than what you just see, right? So who is liable for this? It's actually in between JIT and type system. We believe that these are the one that take about 60% of the time in the startup, doing all the work, trying to prepare all those 4,000 methods to be JITted, and some may be wrong, and some may not be wrong. And interesting enough, this is my first job, being a type system lead. I went to type system guy. Actually, no, my first job was JIT. I had 3 devs. I went to the JIT and say, JIT, we are slow, and we are the reason why .NET code doesn't run fast. JIT say, nah, it's not our fault. It's type system. My second job, I was type system lead. I went to a type system team and said, hey, David, we are slow. What should we do here? And David told me, nah, it was JIT. That doesn't make sense, right? Somebody must be at fault. It turned out to be type system only has 30%, 33%, 1/3 of it. JIT has 1/3 of it. None of them believe that they are the majority of the fault. And the other 1/3 landed in that JIT E interface. Because remember early on that we talked about when JIT generate codes, it comes out type system. It asks many questions to the type system. And then so type system told JIT team, say, if you ask the last question, we will not be so slow. And then JIT actually come back to type system and say, if you answer your question faster, we wouldn't be that slow. Regardless, somebody has to solve the problem, right? So I'm going to ask Sergey to solve this problem to me. Otherwise, we cannot ship.
All right. Thank you. I'll try. Okay, as Mei-Chin noted, the main problem here that I need to solve is the time we spend JITting the code during application startup. If we kind of step back, we think about it, what we do actually, we JIT the same code every single time we run the app. We load the same libraries, we parse same config files and JIT it. And end result, the code, the bit code actually JIT produces is exactly the same on every single invocation. Seems like wasteful. So how about we just cache it and reuse it later? So Engine is a tool that we built for the .NET framework to solve this problem. What it does is pretty much just load an application or a library, and then it compiles every single method it is there and stores the result in the system-wide cache. Next time when application launches or loads one of its libraries, Runtime finds the precompiled code and loads it instead of JITting it again. So let's look at the results. As you can see, the startup time has changed drastically, right? We improved it by 2.3%. It's now 2/3 of what it was before. Looks impressive, right? Okay, we are done here, right?
Not bad, not bad. I know that has some factors. And to go back to the history, this actually happened in what we tried to ship .NET 1.0. The 2 months before we shipped, we found out our performance is not acceptable. One developer actually got called and said he got to solve the problem. That developer's name is Sean. This is the solution we provided, and we just shipped in time.
Right. One thing I want to mention about Engine and its characteristic is fragility. So the code it generates is really just JIT code, and it contains a lot of assumptions that make it very fragile. For example, type layout, right? The JIT makes assumptions about at which offset is each field, or when it makes a virtual call, it needs to know the location in vtable where to find the actual address of the method to invoke. All this makes it very fragile. And then even the data structures that live in CLR, they can change from version to version, and they do influence the JIT code. So what it means is, well, you precompile your code, and then you decided to copy a new version of your application or a new version of the library that the application uses, or maybe just Windows Update installs a new version of framework. What happens then? The cache you had is pretty much invalidated. So just to be clear, there is not going to be any correctness issue, because Runtime by itself has knowledge about that, and it has means built in the cache to resolve those issues. So what will happen is we will just throw away the pre-JIT code and we will fall back to JIT again. And so yes, the code will run slower, but it will still be correct. Well, yes, that's a problem, but how often does it happen? Like how often, for example, Windows updates .NET framework, right? Anyway, in this case, what happens when the cache gets invalidated, Engine service kicks in. It will compile the apps, update the cache, and the app starts running again, fast as before. So seems like it's just an engineering detail, and everything is good. I can tell my boss.
You can keep your job.
Oh, yeah.
Yes. May not keep your finger. So Sergey was happy for a while. Remember we talked about when engine got delivered was .NET 1.0. Do you remember at that time that actually comes with a disk? It's actually not Windows Update. It was actually later on it became Windows Update. Can you do the next slide? He was happy for a while, but his happiness did not last forever. Actually, world is changing on him, and he just didn't know. We were asked about devices that actually is sensitive to battery life. At that time, it was Windows Phone, and then wearables, and actually even laptop. Let's say 15 years ago, laptop lifetime is probably what? Battery lifetime is 2 hours. Today, nobody's going to buy a laptop because the battery life is 2 hours. Actually, the expectation changed. And wearables, HoloLens. Think about HoloLens and spending 30 minutes JITting the code. It's actually not acceptable. And the second one is actually the workload is also changing. Think about servers. When you provision a server images, you build it once. You will want to deploy it into millions of servers. And those server instances, you will expect them to be responsive immediately, rather than those servers had to spend, 10 minutes, 30 minutes generating engine images? It's not okay. The third one is also a killer. Securities. We're generating images on device. How do we know it's not tampered? And our engine services, actually elevated services, how do we know that we won't be hijacked? In fact, Windows actually require all the images, executable images, to be signed. Otherwise, it cannot be trusted. The last one, as we go to .NET Core, we go into Linux. Where are we going to do elevated services in Linux operating system? It is just not going to work. So here I am going to tell Sergey back, sorry, your solution did not last too long.
Well, I guess that engineering detail was a real problem after all. So what we need a new code generation strategy. What we need to do, we need to scale back on those optimizations that we do in JIT that make real bad assumptions. The good thing that those assumptions are real, just used for optimizations, like I said, and they are not fundamental to ahead of time code generation. We can live without them. So, for example, instead of hard coding offsets into vtable, we can just ask Runtime to give us the data and then call on that. So CrossGen is a new tool that we wrote that generates the code which is version resilient. And it's just one library. It doesn't know anything outside of it. So you can replace libraries as much as you want. The code in other places will not get invalidated. As I said, it's going to generate less performant code because not all optimizations are going to be allowed in this mode. The other nice thing about this tool that it can run anywhere. It can run on the target machine where your application will run, or it can actually run in the build lab where the library or the application is being produced in the first place. What it allows to do is that the companies now can actually sign their binaries on their production servers and deploy TLLs that have been verified, can be verified. Right? So let's take an example. Look at the example of the codegen in both cases. As we said, we're talking about virtual codes, and a code to string is a good example. On my right side, you can see code produced by Engine. you can see the fragility I was talking about. Here are the offsets into vtables. This is vtable, this is a pointer to vtable chunk that is used where is vtable stored. Everything is hard-coded in the image. What this means is if you add or remove a method, virtual method from that class or one of its base classes, this code will become invalid and it will crash. Now, on this side is code generated by CrossGen. There are no more hard-coded offsets. What we do instead, we just call into runtime to get an indirection cell, and then we invoke a virtual stop dispatch on it, which will run a little slower, but it will do the right thing. And it doesn't matter what happens to that object, how many methods we add to it, how much we change it, the code will work. Now, let's measure again. One thing I want to mention about this slide is that it contains data for two different runtimes, for .NET Framework and Core CLR. The reason is that engine by itself, it works well on .NET Framework. And it doesn't exist for Core. CrossGen, on the other hand, was built for Core CLR. It works for Core CLR. So what we need to do, we need to compare highs and lows for each runtime separately. Yeah, this is data you saw before for .NET Framework, and this is for Core CLR. What it means in each row, like again, first row is every single method has been JITed at runtime. This is when we precompiled our corelib, system-parallel corelib. We use kind of fragile compilation for it to get better performance results. And then this is actually our shipping configuration. Is all our effects libraries, framework libraries are CrossGen today to improve the startup. And now what I did here is I run CrossGen on every single DLL that was in the application. And this is the end result. As you can see, we got 2/3 reductions here after using engine, and now with CrossGen, we have even better data. I don't know how my boss says, what my boss says about this data, but to me it looks great. I think we are done.
He's always optimistic. So if you go back to last slide a little bit, this slide actually contains many different things. When we first shipped the .NET Core 1.0, we are actually very unhappy because we are a performance team. .NET Core 1.0 is actually slower than desktop because there's no engine, and we only precompile the core lib. CrossGen for framework was actually enabled in 2.0. That is why some of the performance gain that you are seeing in the previous presentation that actually was manifested, some part of startup there as well. So, as I say, engineer is always optimistic. Didn't he just mention the optimization? Didn't he just go to a stop helper? And startup is not impact. Is that the only metrics that we measure? Why don't you go back to the PerfLab, check out all the metrics that we measure?
Yes, Ralph, right. Startup is not the only metrics. Yes. There is another thing, it's called throughput. So let's look at throughput data. Here, we have data from JSON serialization benchmark. This is actually the benchmark that is used by ASP.NET team and by Tech Empower. So what we can see here is, again, request per second for each configuration. First line is all JITed. All JITed, all code is perfectly generated with every possible optimizations that JIT supports. This is our kind of shipping configuration. And this is if I cross-gen everything in the app. Well, yeah, we do have a problem here. We are about, I don't know, 7% slower than in all JIT configuration. So yeah, I guess we just push the problem somewhere else, from startup to throughput. So we need to think about it.
You need to think about it.
All right. Okay, I'm going to think about it. So let's take a look at the code generation technologies we actually have today. Ahead of time, CrossGen. We talked a lot about it today. Generate fast code. Generate code fast for fast startup, right? But the quality of the code is not optimal. Then we have JIT that actually has two code generation modes. One is the minimum optimizations and full optimizations. The first mode, minimum optimizations, is actually the mode that is used when you hit F5 in VS for debugging scenarios. It's for purpose, again, JIT decode as fast as possible. Minimum optimizations, which makes also your code very debuggable and provides great diagnostics capabilities in VS. And full optimizations is what we have in release, right? Everyone knows this. Interpreter, well, we have a few prototypes of that, but none of them actually works well, and it requires a lot of work on the diagnostic stack to support it. So I'm not sure. None of these technologies kind of work by itself. I guess what we can do is combine some of them together. This is what we've done, been working in the last couple of years. This is what Steve mentioned in his talk, codegen, that was shipped in 2.1 as a preview feature. And it's supposed to be on by default in .NET Core 3.0. So before we had codegen enabled or available to us, we at JIT time could compile an IL or a method only once. And only once we could decide what do we do with it. Do we optimize for fast JITing, for startup, for throughput, or maybe for portability? Now, with JITing, we actually can do it multiple times, or at least twice. So what we can do on startup, we use minops, or we can reuse cross-gen code to run the code fast. And then once we reach the steady state, we can recompile the same code and enable all available optimizations. The other part about cross-gen, what we can do here is actually we can embed in our images like some hints for JIT or for tiering system to do better optimizations or generate code more efficiently. So one thing that we kind of still experimenting with is heuristic for tiered JITing. As the slide says, steady state versus startup is kind of a great area. Every single application is very different. We don't have yet an API called start steady state. We don't know yet, so we kind of have to guess. And there are various ways to do that. One is a simple one is just calculate how many times the method has been called, like hit count, and then at some point start recompiling it. Then we can use more advanced techniques like sample profiling or performance counters. For now, we decided to start with a very simple approach, and what we do is as soon as the method is called 30 times, we invoke the tiering system, and it will replace the method with better code, yes. So measure again, and what we see, yay, we are back. So the throughput is good. The startup is good as well. We haven't regressed that because runtime actually picks cross-gen code at first time. So all good. Back to you.
So if you think about this, this is actually very similar to Java's hotspot mechanism, right? When you, if you're not sure if your code is going to be executed many, many times, instead of spending time optimization all the code, we actually took the heuristic of like, generating code as fast as possible, and as method that identified to be executed more frequently, then we try to optimize those methods. And that actually give you a very good blend of startup and also throughput. So this is our codegen journey. We started with pure JIT, and we never ship in that configuration because it's just not fast enough. And we built engine for the desktop, and that did not get us across to the cloud scenario, nor go to Linux. So that's why we get a cross-gen here, right? And then further down, trying to repair the cross-gens degradation, we built tier JITting. What tier JITting can really give you is actually give JIT the freedom. JIT never had the freedom. JIT had to do the work, but must use the most need to use as little as possible resource, but yet have to generate the best code for you. And if that is actually just not going to gel together. So with tier jitting, what it opens up actually more optimization and optimize only the code that matters. So it's just a starting of the journey, not really the end. And this is a cross-gen and tier jitting are the things that is going to ship in .NET Core 3.0. Next slide. So this go back to Sergey.
Right. So we talked a lot about what we've done so far. Let's spend a couple of minutes talking about what we will do in the near future. So everyone knows that Docker containers are super popular right now. In general, .NET applications, .NET Core applications run just fine in those environments. But we did get a few reports from customers, including the presentation from Steve a few hours ago, that if a container is configured with low memory, then applications can run into some issues. So we are working on addressing that. We're going to change some GC heuristic to consume less memory, and we're going to add more configuration options to configure runtime for those environments if our automatic heuristics don't kick in. The other part that is important for Docker containers is the size of the base images. When we precompile assemblies with CrossGen, we store the precompiled code in assemblies themselves, which means bigger size of those libraries, right? So what we want to do for 3.0, we're looking at using partial compilation to reduce the size of the CoreFX frameworks that we ship, and at the same time not to regress startup times, right? Then, as you probably saw in .NET Core 3.View blog post, we're going to ship a new UI stack, WinForms and WPF, right? And UI apps, what they do, what do they require? Fast startup, quick response times, right? So we will spend some time actually optimizing those libraries and precompiling them. And last but not least, we want to ship, make our CrossGen compiler publicly available, so every developer can optimize the applications. I want to quickly show you, I know, 1 minute, what is the right time to use AUT? As you saw, there's always a trade-off, right? So how do you know whether CrossGen is right for you? In this case, yes, PerfView is a performance tool, is your friend. There are a lot of tutorials and help on the GitHub, and this tool is super powerful. It can show you everything your application is doing. We're going to use the NuGet Patch Package Explorer. It's actually a real-world application that has been ported to 3.0 and uses the brand new UI stack. So what do? We start PerfView, obviously. We use collect options to start data collection. We launch our application. Once application started, we start collection, and PerfView will generate an ETL file. As you can see, PerfView can do lots of stuff. It generates lots of different data, sampling profiling, and memory, GC information. But what we are interested in right now are just JIT stats. If you click on that, it will open a new window, contains lots of information about every single method that has been JITted. But I just showed you the summary. So what you see is we spend 2 seconds, or 60% of CPU time, JITting the code. Not good. So again, these numbers are point in time. When we ship the .NET 3.0, the final release bits, these numbers are going to be much lower. Next slide, I precompile the app, run it again. You can see the JIT time has disappeared, pretty much all of it. Like, it used to be 2 seconds, now it's 200, 300 milliseconds. Startup of the application is about 1 second, right? So that's it, what I showed.
Takeaway is performance is hard, and Sergey can keep his job.
Thank you. About the jobs, by the way.
That's right.
About the jobs. Yes. Right. The slides are in a talk, so guys, if you have any questions, please send emails, talk to us. Thank you very much.